the motivation for AFM, because AFM is the most basic tool, and from there we can proceed on to other techniques. So the motivation came from trying to get a better resolution. Now, what do I mean by a better resolution? If I have one small dot and that dot is radiating light, even if that dot is a couple nanometers wide, I'll probably be able to see it. But what happens if I have two different objects and I want to see the separation between them, to resolve between them? So can I see them? So in 1896, so Rayleigh gave a certain criterion, and that is that the separation between them has to do with the wavelength of the light which you are looking at the object. Okay, so the wave-like nature of light creates diffraction, and therefore there's only a certain resolution which we can resolve between two different objects. So the criterion is more or less half of a one wavelength. So if we're looking at with a microscope, doesn't matter how strong the objective is, 50x, 100x, the best lens we have, most focus we have, at the end of the day, if we're using 500 nanometers to look at our sample, so more or less with a traditional available light microscope today, we can resolve 250 nanometer difference between two objects. If they're close together, we will see them as one object. So for example, a bacterium are large enough to see two different ones, and a virus is small enough so we can't really see different viruses. If, of course, they're far away, we'll see them. But if they are less than 250 nanometers, it'll be very difficult to see them. There are today different techniques which try to get a better resolution. One of them is AFM, so we're going to speak about AFM. So here we have optical image. This looks to me like cells. And this is the resolution we see. Now when we scan it with AFM, so we see a much higher resolution. And not only do we see the higher resolution, we also get a 3D mapping. So we get more information. Okay, so how does a basic AFM work? Let's talk about just how it works, and then we'll talk about the concepts. So this is what we call a cantilever, and here is the tip. So we have this tip which gets close to the surface. So here's atoms on the surface, and the tip is getting close to the surface. And what happens when it gets close to the surface? This cantilever deflects. So we have a laser which is hitting the end of the cantilever. It's then the laser deflects onto a detector, photosensitive detector. And this way we're always monitoring what's happening to the cantilever. So when the cantilever is far away from the sample, nothing is happening. The laser will stay at the center. We align it in such a way that in the beginning the laser will stay in the center of the detector. And when the cantilever, when the tip is very close to the sample, the cantilever will start deflecting, and this laser, instead of hitting the middle, will hit a bit up or a bit below. Depends on how the sample, the topography of the sample. So that's our feedback to know what's going on there. Now, how does that help us to get a better resolution? The tip has a very, very small diameter at the bottom. Typically something like 10 nanometers or even less. So our resolution can become really 10 or even 5 nanometers in the spatial resolution. So what happens next? So we have here the tip touching the sample. And we know that it is very, very close to the sample because the laser deflected a little bit up. So let's draw it. So we have this tip here, And let's say we have a sample which seems like this. This area is higher, this area is lower. So now the laser is deflecting onto the detector. I'm going to look at the detector. So now the laser, when we're far away from the sample, it's hitting the center of the detector. When this comes down lower, so the cantilever will deflect, and the laser will probably hit a little bit higher. Now we start scanning. So we have the bottom scanner where the sample is sitting on, starts to move. Now what happens when this area will move to where the tip is? So now the tip feels more force and will have a higher deflection of the laser, will go up. So for this we have a feedback mechanism. That means we tell the system, okay, if the laser is at this height, deflected to this height, that's the point where we always want to keep it. That's our zero position. If the laser went up, so move the scanner a little bit lower until the laser goes back to this position which we set before. It's called a set point. So this way, now we know how much the scanner went down. That's our Z movement. So for each point here, we know how much the scanner is going up and down. And that way we know for every resolution point our Z, and at the end we get a certain map, a topography map. Okay, so let's talk a little bit about the basics, the fundamental basics. So this is a sentence which I like from Feynman lectures. Whoever learned physics, it's a very famous lectures. So he says, if the whole world will suddenly collapse and we have to leave one sentence for the next generation in physics, what sentence should we leave them? So he says the most important sentence in his eyes is the atomic hypothesis. That means that we have atoms, they're like small balls and they repel or attract, and of course that with a little imagination and thinking, so we can from that take that to many applications. So let's see what happens in AFM. So this is a curve which is also a famous curve of the force between particles. When particles, this is the distance and this is the force. When particles are far away, so there is a small attractive force. The minus is attractive force. As the particles start to get closer to each other, so we have a stronger attractive force, and at a certain distance they start to repel away from each other. Now, why does this happen? This is, if you've heard of van der Waals forces, okay, the particles, even though they seem that they're stable, that the atoms are stable, we also learned from Raman that they're always vibrating a little bit. So when the nucleus is vibrating a little bit, the electrons around them are also changing the electric field, and this creates a dipole, and also will create a dipole on a particle nearby, and then it will interact back in each other. So as they are closer to each other, we get this stronger force. So we're going to use this force for AFM, for our advantage. So when the tip, which we saw beforehand, gets very close to different atoms, there's a certain force which happens between them. So in AFM, there's mainly two modes for working. One is contact mode and one is the intermittent mode. Now in contact mode, so what we saw beforehand, this is what we call the contact mode. The cantilever is more or less not vibrating. The cantilever is stable, and it's just deflecting when it feels force from a force from the sample beneath. So here it feels a stronger force, here it feels a less strong force. the more, I would say, new mode which they use today is their intermittent mode. And why is this a little bit better? The intermittent mode, we have the tip, the probe vibrating. And when it's vibrating, it's moving between these two areas, the attractive force and the repulsive force. And this way we can get much closer to the surface. In the contact mode, we can't get so close to the surface, and we'll talk later on about the two techniques. Okay, so here are the two methods for AFM feedback. One is which we talked right now, the standard way, which we call beam bounce. We have a beam which is hitting the cantilever, it's bouncing back onto the detector. And I would say a newer technique is with a tuning fork. So this tuning fork is vibrating at a certain frequency. Mostly we're going to try to vibrate it at the resonance frequency of the fork and the cantilever with and the probe. Okay, so let's go back to here. Here we have, I would say, one major problem when we try to integrate this method with other, even with especially with Raman or with any optical measurements of the near field. Here to know the feedback of the cantilever, we have to have a laser which hits the beam and bounces off. So this can create a lot of interference if we're trying to measure optical or any information which we need to use, let's say, another laser from the surface. While using the tuning fork, our feedback is only from the tuning fork. Now, how does the feedback work here? The tuning fork is vibrating at the resonance frequency. Now, when it gets close to the sample, let's say we have a sample which is right here, when it gets close to the sample, this resonance frequency will shift. So we're going to monitor always this resonance frequency and see how it shifts, the amplitude or the phase of this vibrating tuning fork. So one advantage of using the tuning fork is that we don't have the optical interference, but there are other benefits using the tuning fork. So when using the beam bounce, which we see here, so this is kind of a graph of what happens with time. So here we're far away from the sample. When we get close to the sample, we have what's called jump into contact. Now, why does this happen? For this cantilever to work properly, it has to be very soft, because we want it to feel very soft, to deflect very easily when it gets close to the sample. So when it gets close to the sample, most samples have a small layer of water on it. And this water will cause a very strong force on the probe, and it will just push it down very strongly. So it's called jump into contact. So first it will jump into contact, and then it will slowly go out. Here we can measure the force. And then when we're going out of contact, what will happen is, because of the adhesion with the water, it will take longer for this probe to leave the scanner. The scanner is moving down, but the probe will move a little bit down with the scanner before it totally moves away from the sample. That's because the adhesion of the water, and that the cantilever is very soft. And then it will start what we call ringing, like kind of vibrating, until again it goes back into control. And then again the scanner is always moving. We want the scanner moving at a fast speed. If it moves too slow, we can wait a whole night to see a scan. So again, it hits a different area, and then again it will jump into contact, and again we'll have this whole cycle again. So this is one, I would say, another disadvantage of using the beam bounce.